Okay, welcome to the second chapter of the Logical Foundations of Cyber-Physical Systems course, where we will now be studying differential equations and their domains. In other words, we're zooming into the continuous dynamical systems aspect of hybrid systems. No wonder, if hybrid systems combine discrete dynamics and continuous dynamics, we would do very well to at least start with understanding continuous dynamics before we proceed on to understand discrete dynamics. And again, let me remind you that it's ultimately the multi-dynamical systems principle that makes this easy for us, the phenomenon that we can understand the big thing by understanding one of its parts at a time and put our understanding back together later on. So from a computational thinking perspective, what we will learn today is zooming in on the semantics of differential equations and understand their descriptive power. We will also, for the first time, see an extremely fundamental principle of logic and of computational thinking, which is that there's this important separation and relation between syntax versus semantics. On the modeling and control side, we will understand the continuous dynamical systems aspect, understand, of course, differential equations, but also their fundamentally important evolution domains, as well as a language of choice to describe those representations of the state space on which continuous evolutions can happen. We will see first the logic in action. From the CPS skills perspective, we will be looking at continuous operational effects today. Of course, today's lecture is not and cannot possibly be a replacement for an entire differential equations course, but it also doesn't have to be, because what we're trying to make happen today is to give you a working intuition for playing with differential equations, because for the time being, this, in addition to their precise mathematical semantics, is all that we will need for the subsequent parts of the course, until later in part 2 we will zoom in into a lot more detail into differential equations. And in fact, by design, the first part of the course you can understand very well if you just understand some very simple, intuitive differential equations, in order to give you an opportunity to pick up more of your differential equations knowledge on the go. For that very reason, the textbook chapter number 2 on differential equations and domains also gives you a lot of opportunity with more examples and more background and more principles that you can read at your own pace. Now let's get started. What is a differential equation? Well, it's meant as a model of continuous processes where we have a vector field, y prime of time equals a function of time and the current value y, with also an initial value. So y at an initial time t0 is supposed to have a very specific initial value y0. But what's the intuition of that? Well, let's plot at every point in the state space, here it is, the value of the right-hand side of a differential equation. So for example, here the vector will point this way, here it will point that way, here it will point this way, and so on, as a vector. And then what the intuition is for the initial value is that we pick one, say over here as an initial value, and then a solution of a differential equation is some function that starts at the initial value y0 at the initial time where it is supposed to start, and then, well, follow our nose. Well, not follow our nose, but follow the description of the vector that corresponds to the right-hand side of a differential equation. So follow here and follow this way, always follow the vector chain, basically. In other words, this will be one particular solution of the differential equation that we get when we start at this point. Oh, actually, hold on a second. I think I forgot to tell you what the value of the differential equation is at this point. It's supposed to go this way. No, wait, there's one more I forgot. Over here, the differential equation points that way. And actually, I think over here it points this way. and there it points this way. Oh, I guess I'll never quite be done with this. And that is kind of the point. Differential equations tell us at every point of the state space where the evolution is supposed to go to at the moment. But whatever picture we're trying to draw of this cannot possibly represent all of this faithfully. In other words, this vector field diagram should really show infinitely many vectors at every point of the state space, at which point the diagram will be rather crowded and hard to read. But the mathematical principles of differential equations are certainly understood to be exactly like that. They give us at every point of the state space a description of which particular direction the system does evolve to should it be at this point. For example, this differential equation down here is a model of your car. I'm not sure you recognize it. You might have a slightly bigger car than this one, but the point is, it is describing a admittedly simple part of the motion of your car, namely that the derivative of the x position is the velocity, while also the derivative of the velocity is the acceleration. In other words, as time changes, the position changes like the current value of the velocity, but as time changes, the velocity also changes as the current value of the acceleration tells us. Well, truth be told, cars is slightly more complicated than what I told you right now, but nevertheless, this will be a very good starting point for a lot of our development. And in fact, if you take time to really truly understand the x prime equals velocity and v prime equals acceleration differential equation, you already have a very good start in this course. Now, let's understand the intuition for differential equations in more detail, but let's move for simplicity into a one-dimensional differential equation. We only have one state variable, x, and we have time. And this differential equation here says that the derivative at every time of the x value is supposed to be a quarter of the present value of the x value, and the value at the initial time 0 is supposed to be 1. That means the one thing we already know about how the function or the solution looks is that it had better start at the value 1 at time 0. So it's got to start here. And then, well, intuitively, what the right-hand side of a differential equation tells us is at that point is that the derivative or slope at that point is supposed to be a quarter of the current value, which is a quarter of 1. And one thing we could do very naively is simply follow this for a long period of time. For example, for 8 time units, we pretend the derivative is supposed to be a fourth of the value. So it's supposed to be 1 over 4 times 8 time unit gives us this particular function here. Well, that's if we take one gigantic time step of 8 time units. But well, the mistake we've made is, of course, is to say, well, even if a quarter of the present value, so a quarter is supposed to be the right derivative here, like a little time later, let's say here or there, the value of the function has already changed, and it's supposed to have a derivative that's a quarter of its updated value. In other words, at least at this point here, we made a mistake. We should have done something differently. So at least at this point, we should have said, wait a second, the value is already 2. So if the current function value is 2, then the derivative is supposed to be a quarter of 2, in other words, 1. So right here, we're supposed to go up a lot more than we did. So if we listen to the differential equation here, and again listen to the differential equation here, then here at the latest do we find out that the function value actually needs to increase more. But we still made a mistake, because come to think of it, for example, at this point, we really also should have already listened to the increased value of x, and thus also listened to the, by this very differential equation, x prime of t equals 1 over 4 times x of t, to the increased rate of change that the value is supposed to have. So here we already should have been listening and take the slightly larger slope into account and then take it into account and take it into account. But honestly, that wasn't quite accurate either, because there's this intermediate point, for example, where we should have been listening to the differential equation. And you kind of get the picture now. No matter how often I listen in this discrete fashion with the one step at a time principle of letting time pass for a certain period of time delta, it won't quite be good enough, because even if I keep on doing this, the actual true solution of a differential equation listens to the differential equation at literally every point in time. And indeed, that is why the actual solution of a differential equation will listen to its right-hand side derivatives at every point, and of course will be a continuous function over time, namely in this particular case, an exponential function e power t over 4. But nevertheless, this gives us an important intuition for the concept of a differential equation, that a differential equation listens to having the derivative that equals the value of the right-hand side. It just does so literally at every point in time. But that should prompt you with a number of probing questions. Now, I mentioned this intuition about a vector field, but what exactly is that? And what does it really mean to describe the direction of evolution at literally every point in space? I mean, at least drawing it was quite impossible. Could these directions possibly contradict each other? If I have one direction and right next to it I give another direction and it looks like a great idea, but somehow it doesn't fit together anymore? In other words, the physical impacts of cyber-physical systems simply do not leave much room for failure, which is why we immediately need to get into the habit of studying the behavior and the exact meaning of all the relevant aspects of cyber-physical systems, and certainly we will start with fully rigorously understanding differential equations today. The intuition I just gave you, both in terms of vector fields that we follow and in terms of what happens over time at many points in time, will still be an important intuition for you to carry forward through this course, but we need to become more precise about what differential equations really are and what the solutions are, because otherwise there's just too many risks that we misunderstand what our CPSs will be doing in the end. So let's make it precise. If we have a function f for the right-hand side of a differential equation, which is giving us a vector in the n-dimensional real state space at every point of a domain, where the domain has some subset of the time values and the current state values, where by domain mathematicians mean it's an open and a connected set, so no isolated parts of the set, and it had better be an open set for the definitions to make a ton of sense. Then a function y, which is defined on some interval I and gives us a state value, so a vector in the n-dimensional state space, at every point of this time interval I, is a solution of this initial value problem with the differential equation y prime of t equals f of ty. So the time derivative of y at time t is a function of the current time and the current value, with the initial value condition that the value of the function y at the initial time, t naught, is supposed to be one specific value, y naught. Then this y function is a solution of this differential equation and initial value problem if it listens to that at all times. And that means, first of all, it had better be defined at every time. So the time and the value that the solution takes at time t should be in the domain on which the right-hand side of the differential equation is even defined. Otherwise, it's not a very meaningful construct. Also, since we're talking about derivatives over time, it's a necessity that the derivative is even defined. That means the time derivative y prime at time t exists at every time. And if you were to plug it into the differential equation, it exactly satisfies the differential equation. That means the time derivative of this solution y is actually the value you get if you take the right-hand side of a differential equation and plug in the solution. So it is indeed y prime of t has the same value as the function has at time t, and with the current state being y of t. And so far we merely defined what the solution of a differential equation looks like, but we kind of sort of ignored the initial value condition. Let's make up for that. A solution is only a solution of this particular initial value problem if it also listens to the initial value. That means at the initial time t naught, it has the particular concrete numbers prescribed by the initial value y naught. And any function y that meets these three conditions is a solution of this particular initial value problem. Observe that the solution is in some sense nicer than the differential equation. Because, for example, if the right-hand side function is a continuous function, which in math is written down like this, it's a continuous function from the domain D to the n-dimensional state space of the real vectors, or just think of it as f is a continuous function, then the solution y is a C1 function. That means a 1 times continuously differentiable function. In other words, if the right-hand side is continuous, the solution is already continuously differentiable, so a bit better. And why is that? Well, because if this function is a continuous function and we plug in a value for y which has a derivative, according to the second criterion, well, if it has a derivative everywhere at every time t, then it had better be a continuous function, because every differentiable function is also continuous. And that means the right-hand side here, because f is continuous, and we plugged in a function that is at least continuous, the right-hand side will be a continuous function of time. And since the derivative of y equals this continuous function, I guess the time derivative of y is a continuous function, and is precisely what it means for a function to be continuously differentiable. In other words, the point is that in some sense, solutions of differential equations are nicer, namely more smooth than the right-hand side of the differential equations themselves. But no, if you haven't seen this before, that is okay. It's merely a kind of reminder for those of you who have, and a way to tell you that differential equations do enjoy very nice properties. Let's develop our intuition further by looking into some examples of differential equations. Well, if we have this differential equation here, the derivative x prime at time t has the value a half, and the initial value at time 0 is supposed to be minus 1, then this differential equation system with a constant right-hand side has a solution. I wonder if you can guess it. Well, the derivative is always supposed to be a half. So if we take a function x whose derivative is always a half, then I guess this 1/2 value should be the value that's in front of the occurrence of the time variable. And yes, indeed, x of t being a half times time minus 1 satisfies this initial value problem. So we see a plot of this function over time here. It always has the derivative 1/2, so it always has the constant slope. It always is slanted in the exact same direction everywhere. And now there could still be many functions that look like this. For example, here's another one. But the point with the red one is it simply does not meet the initial condition that at the time 0 it's supposed to have the value minus 1. In other words, this particular minus 1 value here had better fit very well to the initial value condition. Now, that's all nice in terms of intuition, but if we ultimately want to get into the business of rigorously reasoning about it, how can we convince ourselves that this function of time really is a solution of this differential equation and initial value problem? Well, not by plotting diagrams, because as we saw before, they can be somewhat misleading in this world, but by plugging it back into the differential equation and simply checking if it meets the criteria. First of all, this function is differentiable. Otherwise, it would be very awkward to talk about its derivative meeting some values, even though that's possible in Caratio-Dori senses and so on. Let's not go there for this course. So let's plug it back in. The time derivative of a function is the time derivative of how it's defined, half t minus 1. The time derivative of that, of course, ignores the constant offset and just takes the 1/2 as the cofactor of the time, which is a half. And yeah, let's check back what it's supposed to be. It is supposed to be a 1/2. That's a good thing. So they've met. And also, x at time 0, if we expand the right-hand side, gives us 1/2 times 0 minus 1. And yeah, that is the minus 1 value that it is supposed to be. So we've succeeded convincing ourselves that indeed this function is a solution of this differential equation. But now life gets more complicated, because here's another differential equation, the one we've seen before, which is a linear differential equation. The right-hand side is a linear function. The time derivative of x is supposed to be a quarter of the current value of x, and the initial value is supposed to be 1. Well, I'm not sure if you remember the solution, but if not, you can take a moment to try and construct a function that meets these criteria. It's the exponential function e power t/4 that you also see plotted down here. And notice here, we do no longer have the same derivative everywhere, because of course, as the value keeps increasing, the rate of change keeps on increasing because it's a function of the current value. It's 1/4 of the current value. So this keeps on increasing and increasing and increasing and increasing, and if I were to continue it, it would look something like that. Again, we can convince ourselves that this was the right solution by simply plugging it back in and checking it. So let's do so. The time derivative of x of t is the time derivative of the exponential function. Then we remind ourselves, how do you take the derivative of an exponential function? Well, you keep a copy of the differential equation and then take the derivative of the inner argument, t/4, and multiply with that. And the derivative of t/4, of course, gives us 1/4, because that's the only term that that's the cofactor for anything involving time is concerned. And then, yeah, you remember that that just went by the name of x of t, and yes, the right-hand side is indeed 1/4 times the function x of t as the differential equation prescribes. And then the value at the initial time 0 is e power 0, which is exactly 1. So it does meet all the criteria for being a solution. In fact, in this case, it is also the only solution. Here's another linear differential equation system. Right-hand side are linear functions. The derivative of v is w at the same time, while the derivative of w is minus the value of v. And the v is supposed to start at 0, and w is supposed to start at 1. You can take this function and think for a moment what could be a solution of it. V is changing more when w has larger values, but w is changing more when minus v has larger values, which is why v equals sine of t and w equals cosine of t are solutions of this. Let's try and convince ourselves of that. Here is a plot over time of the w value, so cosine, and here's a plot over time of the v function, so sine, and well, they do fit, because in the beginning v starts at 0, as we said, and the cosine function starts at 1, as we said, and v has 0 value. In other words, the w, whose derivative is supposed to be minus the present value of v, which is still a 0, essentially tells us that at the beginning w doesn't change, and after v increased a little bit, well, it begins to change and it keeps on going down because the value of v keeps on going up. Why does the value of v go up? Because simultaneously the derivative of v is equal to the current value of w, but the current value of w is 1, so this is going upwards. But after a little while, the value of the w function has dropped down to 0, which means at that point, because the rate of change of v is w of t, means that if that is currently 0, that isn't changing anymore. But moreover, because the rate of change of w is still minus the present value of v, which is minus 1 at this point, the w function keeps on going downwards and decreasing here, which also means that it becomes negative, and that means, of course, that the v function will now have a derivative that is a negative. In other words, it keeps on going down again. After some amount of time, the w function will have to turn around because the v function has become 0 again, and the derivative of w is minus v of t. In other words, that's currently 0. Another way of visualizing how these functions look like over time is to look at how they look in state space or phase space. So if we plot, leave out time, just plot the v value and the w value, then indeed v, which equals the sine of t, and w, which equals the cosine of t, where this angle here is t, in other words, will have the value that the differential equation prescribes, namely that it keeps on rotating the angle t here, and sine and cosine functions catch up as a value of the angle or time t. Now, if you modify the differential equation to have some constant number omega in front of the 2, then the solutions no longer fit to this, because the derivative of the sine function is the cosine function and not omega times the cosine function. And the derivative of the cosine function is minus the sine function, but not minus omega times the sine function. In order to make up for the presence of the omegas, we need to modify the solutions as well by taking omega into account. So the solutions all of a sudden will no longer be sine of t, but it will be sine of omega t, and it will no longer be cosine of t, but it will be cosine of omega of t. And then, for example, if we check, we will find out that the derivative of sine is the derivative of this function, which in principle is cosine of omega t, but also the inner function derived by the chain rule, which precisely gives us the cofactor omega, and likewise on the derivative of cosine of omega of t. In other words, it is also still, characteristically a very similar oscillation here, but the frequency increases with the value of omega. It keeps on oscillating faster and faster and faster. Many of these types of examples are also written up in the textbook that you can follow at your own pace, depending on how much you already know about differential equations. But let's take the same differential equation system written here and augment it with additional differential equations. X prime is v of t and y prime is w of t, where v and w change in the way they just said. And x and y start at some initial point, x naught, y naught. While v and w do not start at 0, 1, but they start at some initial direction, v naught and w naught. Well, in that case, the solution, I don't want to write it down explicitly, you can think about how you would do it on your own, but in that case, this differential equation system essentially describes the motion of a point along a curve, where v and w are the direction where the point is heading into, x and y, so the x coordinate and the y coordinate, are moving in the direction v and w, but simultaneously the direction v and w that x and y are moving into, according to these differential equations, x prime of t is v of t and y prime of t is w of t, is also rotating precisely as it did in the previous identical differential equation example. In other words, we're moving in this direction, but we're rotating. In other words, we're moving on a circle. This differential equation will indeed become important for us at some point in the future, namely when we're studying the second part of the textbook. Moreover, there's many other examples of differential equations and their solutions you could be writing down. I gathered a few of them here. You should think on your own whether you agree that these are solutions or whether the table is misleading you. But the point I want to make is that if the differential equation is a simple constant function, the solution is a linear function. If the differential equation is a linear function, the solution is an exponential function. We essentially convinced us of those cases a moment ago. If the differential equation is 1 over x, the solution involves the square root. This differential equation already is e power minus x squared. This simple linear differential equation, x prime equals y and y prime equals minus x, gave us the sine and cosine function. The differential equation, which is a simple polynomial, 1 plus x squared as the derivative of x, has a solution, the tangent function. You might recall that the time derivative of the tangent is 1 plus tangent squared. That's where this comes from. And this pretty harmless looking differential equation has solutions that look like that, which are actually non-analytic functions. So if you were to try to represent it as an exponential series with all the derivatives at one point, it still wouldn't be the exact same function. Please don't walk away from this to believe that differential equations would be horribly complicated things, because, hey, if solutions of differential equations are more complicated than the differential equations, then the differential equations are actually very nice and elegant representations of what in reality is a complicated phenomenon. In other words, the actual takeaway message of this slide is that we've just seen for the first time the descriptive power of differential equations. The solutions of a differential equation can be much more involved than the differential equations themselves. That gives these differential equations a lot of representational and descriptive power, because even very complicated processes can be described in simple ways with simple differential equations by exploiting the fact that they're local descriptions of what the system does. They don't tell you what it does in the long term, at every point in time. They just tell you at the moment in which direction the physical process evolves. And that makes it much easier to describe even complicated processes. This fundamental insight about differential equations will actually be something that we come back to in the second part of the course as well. But for now, just remember that continuous dynamical systems, processes that change as continuous functions over time, are, for good reasons, modeled very well as differential equations, because it makes processes simple. Having seen differential equations in action, they're of course fundamental for describing continuous dynamical systems, but on their own they're not quite enough, because even if you write down the most beautiful differential equation in the world, it will need a way of interfacing with the discrete side in order to form a proper hybrid system at some point. In particular, in a hybrid system, we cannot tolerate that a differential equation just keeps on evolving on its own forever, because the poor discrete cyber side would sit quite close by and be horribly bored. In order to prepare for the presence of a cyber site in our cyber physical systems models, we therefore need to already equip differential equations with a built-in way of saying when they're supposed to stop and yield control back to the discrete cyber site again. That's where domains of differential equations come in. So what we need is a way for the cyber side to interact with the physics side, which is why we need evolution domain constraints Q, by which I mean some constraint Q that we attach with the ampersand operator to a differential equation x prime equals f of x, or a differential equation system x prime equals f of x, where the conjunctive notation, the ampersand, means that the system is supposed to obey both the differential equation but also the evolution domain constraint Q at every moment in time. So if you think about this in a picture, if we plot the time and the state x, And if this now corresponds to some evolution domain constraint, then a solution of this continuous dynamical system with the differential equation and the evolution domain constraint is a function that will take us from some initial state to some final state by always respecting the differential equation, but also such that it always respects the evolution domain constraints. In other words, it remains within inside this green region at all the times. It could evolve for a little bit of a longer time because it still meets the differential equation at every point in time, and it's still in the evolution domain constraint at every point in time. But if the system were to try to continue that and go all the way to time s, then even if at that time s you still happen to be inside the evolution domain constraint, the whole behavior from here to there still does not meet the criteria fitting to x prime equals f of x ampersand q, because it cheated. It went within the evolution domain constraint fitting to the differential equation, but all of a sudden it cheated and went into states that were outside the evolution domain constraint. That is what it's not supposed to do. So even if it ultimately comes back into the evolution domain constraint, it has already left it in between, and it isn't supposed to do that. In other words, in this particular case, the longest behavior that the differential equation with its evolution domain constraint can have from this particular initial state is all the way until here, but not any further. Well, that's all nice, but maybe we should become a bit more precise about what is this q supposed to be and what is this f supposed to be. So let's make some examples first. X prime equals v, that means the position changes with velocity. V prime equals a, that means the velocity changes with acceleration. And t prime equals 1, well, that means t changes as time does. In other words, t is a clock variable. And if we now attach to that an evolution domain constraint that time is supposed to be less or equal epsilon all the time, that means all of a sudden we can follow this differential equation system, but at most until time epsilon. Because beyond that time epsilon, we would be violating the evolution domain constraint that the clock variable is supposed to be less or equal epsilon. Could be evolving for less than epsilon. That's okay, but not for longer than that. Similarly, the evolution domain v greater or equal 0 attached to the exact same differential equation system will instead say that we can follow this accelerated motion along a straight line, but at all the times does our velocity have to be greater or equal 0. We can't have solutions of this continue until the velocity is minus a million or something like that. We've got to stop at velocity 0 at the latest. At this point, I invite you to think about the question, how can it ever happen that we start at velocity 10 but suddenly we're at velocity 0? Here's another differential equation system with, you could almost call it an empty evolution domain constraint. Just true, by which I mean there is no actual constraint, because true is always satisfied. The criterion of true being true is always met. For example, this differential equation here says x prime equals y, and y prime is x plus y squared. In fact, later on, we will often leave out this evolution domain constraint from our notation, but can always pretend it would really be there, just abbreviated. But now let's really become more precise after having seen these examples. What can we write down on the right-hand side of a differential equation exactly? And what can we write down in the evolution domain constraint exactly? So first, let's define the terms that we can write down on the right-hand side of a differential equation. We will probably need a way of mentioning variables, x, y, and z. We may also need ways of mentioning constants, like 5 or 1/2 or things like that. We will also need ways of adding terms on the right-hand side, for example, to say x plus y, And we will also need ways of multiplying terms on the right-hand side. For example, in order to say omega times y. In other words, these terms give us polynomial terms. Now, having done so, these are just syntactic expressions. A computer can represent them very well, but our next question, in order to make cyber-physical systems and their continuous dynamical systems fundamentally precise, we should ask ourselves, well, what do these syntactic constructs that a term can look like be? Well, syntactically, a term could be a variable, or it could be a constant, or it could be a sum of two terms, or it could be a product of two terms. In other words, it could also be, because E itself is the gain of this form, it could be a sum of which the left-hand side is a variable and the right-hand side is a sum, and then the right-hand side of that is a product and all kinds of things. But we need to become precise about the question, what do they really mean? Well, the constants should mean themselves. The number 5 is 5 and end of the story. The funny plus symbol, but that of course we mean addition of real numbers. The dot symbol, by that of course we mean multiplication of real numbers. So the meaning of a term should give us a real number at the end of the day, because it fits really well with what differential equations want on the right-hand sides. But what's the meaning of a variable? Well, in any application, we might have some intuitive meaning attached to a differential equations variable, but that's not what we mean by meaning of it. What we mean by meaning of it, because the meaning of a term we just determined should be a real number, should also give us a real number. But which one? I mean, the whole point is that it's changing along a differential equation. But if we fix a state in which every variable has a current real value, then of course in this state the semantics of the term is just defined by evaluation. Let's define that properly. So what we have is that the value of a term, E, in a state that assigns a real number to every variable, in other words the state is nothing but a function, omega, and the value of the term E in this particular current state of the system is a real number that we denote like so, omega evaluated E. And we define this by induction on the structure that the term could have. Well, our syntactic grammar says the term is either a variable or a constant or a plus term or a dot term, so let's define one value for each of those cases. The value for a term that happens to be a variable in the state omega is simply given by the state omega. That's the entire point of the state. So in other words, the value when evaluating a term that's the variable x at the state omega is just whatever the state tells us that the current value of x is. The value of a constant, like 7, is of course precisely the constant itself. And the value of a plus term, E plus E tilde, is just whatever happens is a real number when we evaluate the left-hand side term in the state omega, and then we evaluate the right-hand side term, E tilde, in the same state omega, and we add the real numbers that we get from the left and from the right. The value of a product term in a state omega is the real number that we get when we evaluate the left-hand side term in the state omega, we evaluate the right-hand side term in the state omega, and we multiply the two resulting real numbers. This definition defines a value for every term because, well, every term is built out of these constructors, and each of those cases tells us exactly what the value is. In some of the cases, we may have to look at what the value of its subterms are, but ultimately we will be done with that because ultimately the term will have to be either a variable or a constant. For example, with that, we can ask ourselves, in a state where the value of x has the number 5 content, we can ask ourselves, what is the value in the state omega of the syntactic term 4 plus x times 2? Well, think about it for a second. Of course, the value of plus by this line is supposed to be the value of the left-hand side plus the value of the right-hand side. But again, by the last line, the value of the dot is supposed to be the product of the two values. In other words, since the value of 4 had better to be 4, and the value of 2 had better to be 2, all we need to do is here look up the value that x has in the current state. Yeah, I remember, that was 5. And then compute 4 plus 5 times 2, which is usually 14. That's all nice. I guess we forgot about something. I forgot to mention x minus y as an expression in the term language. That's kind of awkward. We need them, for example, for describing the differential equations for rotation. But do we really need to add them? And the point is, no, we don't. And that makes our lives easier if we keep the language as simple as possible, because that simplifies our analysis and understanding of it later on. Because if we want x minus y, we already have it, just in a slightly more complicated syntactic version, as x plus the constant minus 1 multiplied with y. So in practical applications, we're happy to use x minus y, but in the theoretical investigations, we pretend we don't have it because it could have been expanded. Likewise, what about x power 4? I also didn't put that in the language. That's for the same reason, really, because we already have x power 4 indirectly, because all that we need to do is write down x times x times x times x. That was easy. What about x power n? Same deal, right? All we need to do is write down x times x times x times x times x. Whoa, when do we stop this? The point is that we now need to stop writing down x times x times x times x after we've done this n times. But if n is a variable, we don't really exactly know when to stop. And that's kind of the point why these terms define polynomials. So we can have any arbitrary fixed powers, x power 17, x power 999, but not exponentiation x power n for a variable n. That was how we understood the values of terms. So in order to write down evolution domain constraints, we don't just need to compute values, we need to impose conditions on them in order to check whether the current state is inside those conditions. That leads us to first of the logic. The formulas of first of the logic are defined by the following grammar, where formulas P and Q are built out of any of those constructors, where, for example, E greater or equal E tilde compares two terms E and E tilde that we just defined a moment ago. For greater or equal comparison, E equal E tilde, of course, we'll check whether they're equal. The logical negation will invert the truth value P and Q, of course, to be true if P is true and Q is true. P or Q, P implies Q, P by implies Q, or P is equivalent to Q. And more interestingly, for all x P, what's supposed to mean that P is true for all values of x, that could be any real numbers, and exists x P, supposed to mean that there is a value for x such that P is true. But again, these are just some syntactic representations, and in order to rigorously define what we're supposed to mean by them, we again need to define the semantics of it. And that's where the previous approach doesn't exactly quite work, because in terms we said the meaning of a term is, given a state, the real number that it denotes by evaluating it. Formulas, of course, are not supposed to evaluate to real numbers. They're supposed to evaluate to true or false. And in fact, all that we need is to, given a state, have a way of defining whether the formula is true in the state. And then we do it like so. So the semantics of the first order logic formula is given by a definition for when it is true in which state. So if omega is a state, then we write omega turns to LP to say that the formula P is indeed true in the state omega. So it's just some arbitrary formula. It's one that's really true here. And we can define this inductively again by, for each of the cases that syntactically the right-hand side could have, based just on the syntactic structure of the formulas themselves, we say that in the state omega, an equality E equals E tilde is true, if and only if, well, if we evaluate the left-hand side term in the state omega, we get a real number. If we evaluate the right-hand side term in the same state, we get a real number, and these are the same real numbers, then the equality is true in the current state omega. Likewise, E greater or equal E tilde, that's true in the state omega, if and only if, when evaluating the left-hand side term, we get a real number that's greater or equal to the value that we get by evaluating the right-hand side. Now, in the state omega, the logical formula not P is true. Well, by that I mean the formula P is not true in the state omega, which means it's precisely not the case that P is true in the state omega. So if P is not true, then not P is true, and vice versa. For a logical conjunction, P and Q, they're true in the state omega, if and only if P is true in the state omega, and also Q is true in the state omega, obviously. A disjunction P or Q is true in the state omega if P is true in the state, or if instead Q is true in the state. A implication P implies Q is true in the state omega if, in classical logic, either the assumption P is not true, because false implies anything, or the right-hand side of the implication is true. And the most interesting cases are those of the quantifiers for all and exist, because in the state omega, the logical formula for all xp is true. Well, if indeed, for all the particular concrete real numbers that we could choose for the value of x, in the state that looks like omega but has the value variable x modified to be the number d instead, in all of those states is the formula P true. And likewise, in the state omega, is the logical formula exists xp true if there is one real number d, such that if we change the value of the variable x to be d from now on, then in this modified state is the formula P true, where the modified state really exactly is the semantic modification. So this funny notation omega xt is a state, and that means for every variable y, it's supposed to give us a real number. And if we ask it for the variable y that is exactly identical to the variable x, then we of course give back the value d that it's supposed to have from now on. But for all the other variables y, we just simply give back the state that it used to be a moment ago. In other words, what this is doing is to say that for all xp is true in the state, if p itself is true for every real number modification of the value of x, and exists xp is true in the state if there's one way of modifying the value of the variable x to be p instead. There's something slightly subtle going on here. Namely, your first instinct might have been to simply copy, paste, and plug in the real number value for the variables x. But strictly speaking, that isn't quite okay, because you would all of a sudden need a syntactic representation for every real number. And that's kind of difficult, because how many real numbers are there? Uncountably many. Whereas syntactic expressions are supposed to be represented on a computer, which means they're inherently generated in finite ways. That's just a nuance that is of interest in logic. Let's try and understand some of the notations for it. This notation, given the state omega and the logical formula P, this omega satisfies P, omega turns to LP, we read as the formula P is true in the state omega. If we leave out the state, then this says P is valid. And And by that we mean that the formula P is true in all states. No matter what state omega you choose, it's true in it anyway. And that's kind of the intuition behind this notation, that if the state wasn't important, we might as well leave it out. But these are very important formulas for us in the long term. Formulas that are true in some particular state, they're very important for understanding the evolution domain constraints of differential equations. But the formulas that are even valid are going to be useful for us in the long term, because these are the ones that apparently don't depend on what particular state we talk about in the system. So we can rely on them being true no matter what state our car is in, for example. For evolution domain constraints, it's indeed super useful to use the following notation: the set of all states where P is true, semantics brackets of the formula P, which is the set of all states omega in which the formula P is true. So for example, if we take a logical formula like there is a y such that y squared is less or equal to x, we can ask ourselves, is it true in a state? But we'll also have to say which state it is that we're talking about. So for example, if we are talking about a state omega in which the value of the variable x is 5, then yep, that's true. Why? Well, because for the value of y, we could have chosen the number 1 such that 1 squared is less or equal to 5. That checks. So indeed the formula is true here, but in the state where x has the value -5, so in the state nu, it's not true, because it's really hard to find a real number whose square is less or equal to -5, because squares are greater or equal to 0 in real numbers. This gives us all we need in order to rigorously define the semantics of differential equations with evolution domain constraints. So a function phi of an interval from 0 to r that gives us a state at each of any one of them. What was a state? A state is a function from variables to real numbers, which means a state is something that gives us a real number for every variable. That makes some sense. A state of the system would have to tell us what is the position, what's the velocity, what's the acceleration, if these three are exactly the variables we care about. So, but a function that for every time between 0 and r gives us the state that the system has at that time, for some non-negative duration, satisfies the differential equation x prime equals f of x with the evolution domain constraint q, and we just write that like so, if these conditions are all met. So time derivatives had better exist when we're talking about solutions of differential equations. So first of all, this derivative exists, and it's also equal to the value that the x prime differential variable has at the time z. In other words, the value of the function at any time z of x prime is supposed to be exactly the time derivative that the variable x has at that time as time changes. Second of all, with this apparently being the value that we use for x prime, the formula x prime equals f of x, just understood as a formula, and the formula q from the evolution domain constraint, the entire thing is just a formula, is supposed to be true at the state that we get at time z for all time 0. And also, the differential equation isn't supposed to change stuff that isn't talking about it, which means at any time z, the value agrees with the initial value at the initial time 0, except for the variables we're changing. So except for the state variables x that apparently the differential equation is talking about, and also the x prime differential variables, because, well, we just changed them around. So in pictures, what does that mean? That means a function such as this black curve here, phi, is a solution of the differential equation at every moment of time. For example, at this time z here. So if we compute the time derivative at time z of the black curve, it gives us a line that indeed agrees with what the right-hand side of the differential equation has as a value at that point. And we're also inside the evolution domain constraint at every point. But in particular, it agrees with the derivative that the right-hand side of a differential equation prescribes is supposed to hold at this time z, and at that time z, and at the other time z, and in fact at all the times z along the solution of the differential equation. Now we walk away with an understanding of differential equations and what the precise solutions look like, what the precise solutions of differential equations with evolution domain constraints look like. And we summarize what we've seen today. First of all, we've seen the syntax of the terms that we will be using: variables, constants, addition, multiplication, out of which we remember other things can be defined. And these can be used on the right-hand sides of differential equations or also of differential equation systems. We've defined rigorously what the shape looks like for the logical formulas that we're using for evolution domain constraints. Comparisons for greater or equal, of course less or equal and less than and so on are all definable out of the operators. Equality, not, and, or, implication, if and only if implication, for all quantifiers and exists quantifiers, which maybe are less relevant for evolution domain constraints, but will be pretty fundamentally useful in the long term and really belong in the first order logic anyhow. And most importantly, these are put together to give us differential equations with evolution domain constraints, which are the fundamental building blocks for the continuous dynamics of cyber-physical systems. And moreover, we've not just given these a syntactic representation, but for each of them, we've given a unambiguous mathematical semantics for them. For terms, their meaning is that in every state, they have one particular real number value. For formulas, the meaning is that in a state, they're true or false, or another way of looking at that is, for formulas, we need to know what is the set of all states in which it happens to be true. And for continuous programs or differential equations with evolution domain constraints, we've directly defined from which initial states can they go to what final states by following the differential equation, observing it everywhere, and by observing the evolution domain constraint everywhere.